Welcome to the lesson. Effects of drive shaft stiffness on launch performance. In this lesson, we will study the target sensitivity response of different drive shaft stiffnesses, specifically in the driver's C-track frequency response. As demonstrated in our previous chapter, half-shaft stiffness values can give rise to certain low-frequency vehicle shakes, especially during torque wind-up of the driveline. These resonances, coupled with other suspension resonances, can cause nuisance at the driver interface locations such as C-track and steering wheel, leading to poor drivability. Therefore, it becomes critical to tune the driveline systems, like drive shaft stiffness, to deliver a desired frequency range sensitivity, which can be evaluated and balanced with other vehicle attributes. To achieve this, we can study the dynamic influence of the rotary stiffness on launch performance and driver experience by doing a simple frequency evaluation. Back in our model, we can easily identify the driveline architecture as a front-wheel drive system. Let's perform the study from Chapter 3, this time to observe the effects of drive shaft stiffness on C-track sensitivity by plotting the frequency response of the car body frame. Recapping, we defined a desired acceleration performance of 0 to 100 km per hour in 8 seconds, and analyzed different iterations in which the stiffness values of the drive shafts are changed. For the purpose of this study, and based on results from Chapter 3, only iterations 1 and 2 will be used. It is assumed that the rest of the vehicle parameters remain constant during the evaluations. To observe the effects of vehicle launch vibrations with different drive shaft stiffnesses, driver interface response such as C-track response can be evaluated. To plot the C-track response, click on the 2D vehicle car body and observe the longitudinal acceleration response of the car body frame from the variables window as follows. C-track sensitivity analysis can also be done by plotting the frequency response of the car body frame using a fast Fourier transform. Let's compare this with the half-shaft responses from Chapter 3. As observed from the FFT plots, the frequency of oscillation of the drive shaft is at 10 Hz. The same response is also observed on the target location C-track. If during a certain scenario in the design phase of vehicle systems, this is not a desired frequency at which the drive shafts rotate and may cause unwanted vibrations in the vehicle. The drive shaft oscillations may also amplify other system resonances, causing higher target responses. In iteration 2, the drive shaft stiffness is increased significantly to observe the change in frequency of oscillation. As expected, an increase in stiffness causes an increase in frequency and decrease in amplitude of oscillation from 10 Hz to around 16.6 Hz. The 16 Hz frequency response follows at the C-track as well, which shows that the drive shaft vibrations can transfer to the target location. We conclude that driveline oscillation during vehicle launch can excite driver interface location, leading to unwanted vibrations. An increase in drive shaft stiffness increases the frequency of oscillation and reduces the amplitude, where a similar behavior is seen on the C-track. In the case where drive shaft vibration amplitude is low, but a higher C-track vibration is observed, may indicate an interaction with other system resonances, such as suspension frequencies. Further tuning and refinement analysis may be required in that case to evaluate the effects of systems interactions.